Welcome to OBD2 Session 2. I hope you got a chance to watch the Session 1. We're going to pick up from right where we left off there. This one is going to be looking at the catalyst efficiency. The diagnostic executive or the task manager is going to run this test once per drive cycle. If the test gets interrupted, it won't run the test. It has to test the oxygen sensors first. If there is a code set for the oxygen sensor, it will not run the catalyst efficiency test. There are people who drive their car for months, years with an oxygen sensor code. Chances are that when they finally get that oxygen sensor replaced or the problem repaired, whatever it is, within a few weeks, check engine light's going to come on and they're going to have a code for a degraded catalytic converter. The reason is they wanted to save $100 or $200, whatever it is, by not replacing the O2 sensor. And in taking so long to do that, they burned out a $700 or $1,000 catalytic converter. Requirement of OBD2, they have to monitor the primary catalytic converter, which most all the time is going to be your first catalytic converter. The way that they're going to monitor it, the diagnostic executive is going to look at the oxygen sensor in front of the catalytic converter, which is being used for fuel trim. They don't maintain exactly even. It goes rich, lean, rich, lean, rich, lean, meaning the voltage is going to go down to at least 200 millivolts. It's going to go up to at least 800 millivolts, constantly switching back and forth. If you have a catalytic converter that's good, it's lit off, the oxygen sensor behind the catalytic converter should be showing a steady voltage greater than 450 millivolts. When the engine is running at stoic, there's going to be about 2% oxygen left over. And that's where the oxygen sensor is going to be switching back and forth as we go slightly lean, slightly rich, slightly lean, slightly rich. The oxygen content behind the catalytic converter is going to be between 0.5 and 1%. To an oxygen sensor, that's going to appear as a rich condition, so we're going to see a steady voltage greater than 450 millivolts. When the rear O2 sensor, or your post-catalyst O2 sensor, begins to generate a voltage about 60% of what the oxygen sensor is in front of the catalytic converter, your catalytic converter is now degraded to the point your emissions are going to exceed 1.5 times the FTP, and it sets the code. We have two continuous monitors on the car. We talked about the fuel trim monitor in session 1. Our second continuous monitor is going to be our misfire monitor. California Air Research Board did their research. They found that there was a lot of degraded catalytic converters driving around California. As they investigated that, what they found was the #1 killer of the catalytic converter was a misfire. The purpose of OBD2 is to protect the catalytic converter, so we're going to have a misfire monitor. This one again is a continuous monitor, just like our fuel trim monitor is continuous. They're typically going to be using a high-resolution crankshaft or camshaft sensor that's going to give multiple pulses during the power stroke. The computer wants to see the crankshaft speed up and then slow down as they go through the power stroke. If it doesn't see the crankshaft speed up, it's going to determine that that's a misfire. It is not going to tell you if it's due to an ignition problem, a fuel problem, or a mechanical problem. It's just going to look that there's a misfire, and it's going to set a code for the misfire. So I said it was a continuous monitor. Is it really a continuous monitor? All engines misfire on a cold start. When you start the engine up cold, until the engine reaches a certain temperature, and I don't know what temperature that is, and my guess is it's going to vary from one manufacturer to the next, there'll be no misfire monitoring during that cold engine operation. If your fuel level is below about 15%, again, they disable misfire monitor because as you make a turn or come to a stop or go up a hill, fuel's going to slosh over, the pump goes high and dry, sucks some air into the system, and again, you're going to have the misfire. The last condition I'll talk about is a rough road. If you're driving down a road that has a lot of potholes, as a tire drops into a pothole, it's going to want to slow the car down, which is going to slow the engine down. If that's during a power stroke, the crankshaft is going to slow down instead of speed up, and the computer would flag that as a misfire. The computer is going to communicate with the analog brake computer, the computer being the engine computer, or the PCM, is going to communicate with the analog brake computer. As the analog brake computer is watching the wheel speed sensors, it sees variations there. It's going to determine that you're on a rough road, it will let the PCM know, and they're going to do one of two things. Either they will disable misfire monitor, or on some manufacturers, if it's an automatic transmission, they will unlock the torque converter clutch so that the road condition has very little effect on the engine. A 15% misfire is going to cause the check engine light to flash. Whichever cylinder is misfiring, it will set the code. So if it's cylinder number 2, it's going to set a P0302. Check engine light's going to be flashing, letting you know that there is a misfire. The reason they're going to flash that light at you is that they want you to back out of the condition, whatever's causing the misfire. If you have a 2% misfire, then it's going to require 2 trips. And what they're looking at is the computer's going to look at X number of counts. So let's say that it's 100 firing events for a particular cylinder. If it fires 15 out of those 100 times, that's going to be a 15% misfire. That's going to set the code immediately. If it's somewhere between 2% and 14%, it's not a severe enough misfire to cause catalyst damage. That's going to require 2 trips or 2 tests before it is going to set the code. Once you have your misfire and the check engine light's flashing at you, the other thing they're going to do is they're going to shut the injector off. They will occasionally turn the injector back on to see if the misfire has gone away. If the misfire goes away, then they will re-enable the cylinder, the light will stop flashing, and it'll be a steady light until the misfire reoccurs. Now, when I tell you that they're protecting the catalytic converter, that they're going to shut the injector off, I have had multiple technicians show me. I had one guy videotape it, and it was on a Ford. It had a steady misfire, and Ford continued to pump fuel into that cylinder. Again, I want to stress what I'm telling you. This is what the law says to do. They have to protect the catalytic converter. It may not necessarily be what you see happen. Our EGR system monitor, this is going to be a 1 test per drive cycle, or they're going to attempt to test it just once per drive cycle. However, it's not just one quick test. There's several different tests that they may run. We're going to talk about these 3 tests. On our session 1 video, I talked about that they have a passive test, an active test, and an intrusive test. This is where we're going to see those 3 tests occur. I hope you're familiar with the engine operating, because if you're not, this is going to be really hard to be able to follow. So this is test number 1. This is going to be a passive test where the diagnostic executive is just watching what's happening. If the intake air temp sensor is located in at the intake manifold, as the EGR valve opens, it's going to raise the temperature in the intake manifold. The computer is going to look at that temperature increase, and it's going to calculate EGR flow based on that temperature change. If the intake air temp sensor is not in the intake manifold, let's say it's up in the air cleaner housing, then the computer will look at the MAP sensor. Steady state cruise, EGR valve is commanded open, manifold pressure should go up. Again, the computer is going to look at that manifold pressure increase, calculate EGR flow based on that. If it doesn't have the intake air temp sensor in the intake manifold, if it doesn't have a MAP sensor, but it's using a mass airflow sensor, steady state cruise, EGR valve opens up, the exhaust gas is displacing some of the air coming into the engine, so you should have a decrease in mass airflow sensor reading. The computer is going to look at that decrease in mass airflow, calculate EGR flow. I want you to pay attention that we are calculating EGR flow. We are not measuring the EGR flow. Ford is the only manufacturer that I've ever heard of that actually measures the EGR flow with their DPFE. However, all of the Ford techs that I've talked to, if there's a code with the DPFE, it's normally a faulty DPFE, not a plugged EGR passage. Second test, this one's an active test. While the vehicle is driving down the road, steady state cruise, EGR valve is open. The PCM, so this is the main part of the computer that's controlling the timing, the fuel. Visualize you're using your laptop and you're working with an app and you have the antivirus going in the background. So this is where we've got to differentiate that even though it's the same computer, we're talking about 2 different apps. So the one app running the engine, second app running in the background is going to take over. Visualize. Vehicle's driving down the road, steady state cruise, EGR valve is open. because the exhaust gas is going to displace some of the air coming in, the computer is going to decrease the injector pulse width because we have less air and we still want to maintain stoic. The task manager or the diagnostic executive is then going to close the EGR valve while the PCM still thinks it's open. That's going to cause a lean condition. O2 sensor voltage is going to decrease. Short-term fuel trim is going to start climbing. The task manager is going to look at that rich correction and calculate EGR flow based on that. So on our first test, we were calculating EGR flow. On the second test, again, we're calculating EGR flow, not actually measuring. Third test. On this test here, during a deceleration, we're going to be going from 55 down to 20 or 60 miles an hour and decreasing. Your foot is off the throttle. You're not hitting the brake. No AC, no rear defogger turning on or off. While you are doing what most people call is compression braking, you're not actually compression braking on a gas engine. You're actually vacuum braking. Manifold vacuum is the highest, meaning pressure is the lowest during deceleration. The task manager is going to command the EGR valve open during this deceleration. It's going to look at the pressure change in the intake manifold when the EGR valve is opened up, and again, calculate. Now, if the person is paying attention to their vehicle slowing down from this vacuum braking, as you increase the pressure in the manifold, it is possible, not likely, possible that they could feel that change. That's what classifies this as an intrusive test. So we just went through 3 different ways that the computer is going to calculate EGR flow in order to determine that the EGR circuit is working correctly, not just electrical circuit, but also the passageways. Most common problem with low flow on the EGR valve is carbon building up. The carbon is going to build up where the exhaust cools down, so around the intake manifold. As that builds up, then you're going to get this code for low flow on the EGR, and now you got to figure out a way to get that carbon cleaned out of there. Because we're only calculating the EGR flow, they're not going to set the code in 2 failures. They're actually going to run multiple tests. They're going to average the readings to be able to set the code. Our secondary air injection on the newer cars, all the secondary air systems that I've seen is an electric air pump that's going to pump the air into the exhaust manifold. On a cold engine, we're going to run with a rich air fuel mixture, meaning we're not going to burn all of the fuel that is in the cylinder. By shooting air into the exhaust manifold and having that air in the exhaust manifold when the exhaust valve opens, we'll finish the burn in the exhaust manifold. Most everything that I've read says this will lower both hydrocarbons and CO. I have a hard time believing that this is going to convert the CO into CO2, because I think we need some sort of catalyst to make that happen. But it's definitely going to decrease your hydrocarbon emissions, finishing the burn in the exhaust manifold. By finishing the burn in the exhaust manifold, it's going to heat the exhaust up faster, it's going to heat the O2 sensor faster, it's going to heat the catalytic converter faster. So this is a really good emission item. However, it's kind of an expensive emission item. For most all the manufacturers, they're only going to put a secondary air pump on there if they have to, except for Volkswagen. Volkswagen puts it on just about everything they build. To test this, vehicle running, diagnostic executive is going to take over fuel trim, make it 10% rich. O2 sensor voltage is going to come up. They're going to kick the air pump on for a few seconds, watch the oxygen sensor react to that, and system's working. This is where we were on the OBD1, just looking at the purge solenoid. Now we're going to be checking this evap system for leaks. And this is your fuel tank. And this is one of the most common codes that it's going to set. And it's going to be either, typically, it's the fuel cap is not sealing anymore, or either the purge or vent solenoids that have gone bad. 1996 through 2000 model years, they had to be able to detect a leak as small as 40 thousandths. Starting in 2001, they decreased that. They had to be able to detect a leak down to 20 thousandths. I have heard from a couple different classes that I've gone to that they have a new standard coming out of detecting a 10 thousandths leak. That's the reason I have the question mark there, is because I've heard about it, but I haven't heard that it's actually out, or if it is out, what year it came out. Looking at this, and you're thinking, oh, it went from 40 thousandths to 20 thousandths, and that's half the size. When we're talking about a hole, a 20 thousandths hole is actually 1/4 the size of a 40 thousandths hole. And then when we get down 10 thousandths, it's a fourth again. So we're talking about really small leaks that this has to be able to detect to prevent hydrocarbon emissions from entering the atmosphere. When they put the PCV system on an engine, the hydrocarbon emissions that were in the crankcase, that we were using a draft tube to pull them out and just send them out to the atmosphere, when they started running them back through the crankcase, we reduced hydrocarbon emissions on the car by 20%. When they sealed up the fuel tank, we reduced hydrocarbon emissions off the vehicle by another 20%. This one is critical for reducing hydrocarbon emissions, which is going to contribute to our photochemical smog. Manufacturers also have to monitor purge volume, and here again, the manufacturers have gotten away for quite a while of not monitoring as near as close as they were supposed to be. I've heard several different things of how they're going to do it. The one that makes the most sense to me, if the car's been sitting for a length of time, our charcoal canister is going to be full of hydrocarbons. Start driving the vehicle, engine reaches a certain temperature, and now we're going to purge the charcoal canister. That's going to create a sudden rich condition. O2 sensor voltage is going to go up. Short-term fuel trim is going to go down. Computer's going to look at that fuel trim change and determine what the volume is. If you just stopped at 7-Eleven and got yourself a big gulp, the charcoal canister is empty, your car was off for more than 10 seconds, so when you start it back up, it's going to attempt to run this test again. Without the fuel vapors in there, when it goes to purge, it's a vacuum leak, so it's going to cause the system to go lean. With the system lean, the O2 sensor voltage will go down, fuel trim will go up. Again, the computer can determine or calculate your purge volume by that reaction. So it didn't matter if it went rich or if it went lean, as long as it saw the change in there. Taking a look at our enhanced evap system, which became mandatory in 1996, we have down here is our charcoal canister. Similar canister to what we had back in the late 60s, early 70s. The purge solenoid, once we went to computer controlled, the computer controlled how much purge there is. With the enhanced system, they also added the vent solenoid, which is this one down here. Fuel tank. The fuel tank level sensor now goes to the PCM. PCM wants to know exactly how much fuel is in there. And we added a pressure sensor. This right in here is going to be a liquid separator, and it's also going to be a rollover valve. During our purge cycle, vapors from inside the fuel tank, because our cap is sealed, these vapors are going to come over. They're going to be captured in the charcoal canister. If there's any air in the system, the vent is going to let the air go out, but the hydrocarbons are going to be captured by the charcoal canister. When we go to purge, air is going to come in through the vent solenoid. As the air movement goes through here, it'll pick up the hydrocarbons, and we're going to burn the hydrocarbons through the engine, not allowing them to go into the atmosphere. The diagnosis, or when the computer goes to run a diagnostic, it is going to open up the purge solenoid. It's going to close the vent solenoid. Now we're going to have a vacuum coming into our fuel tank. The computer's going to watch this pressure sensor. It's going to look at how much fuel it's in. Depending on how much fuel is in here is how long it'll take it to pull into a vacuum. If the system won't pull into a vacuum, it's going to set a code for a large leak. If the system pulls into a vacuum, it's then going to shut the purge solenoid, keep the vent solenoid closed, and watch to see if it'll hold a vacuum. If it won't hold a vacuum, it'll set a code for a small leak. The manufacturers have also started using what they call key-off natural vacuum. As you're driving down the road, the fuel tank is going to warm up. When you shut the car off, they're going to close this vent solenoid, which our system is now sealed. As this cools, it's going to condense, and that'll create a natural vacuum. That test will be run after you shut the car off when you walk away. This is what they're using to try to detect the smaller leaks. Some of the manufacturers, instead of having a vent solenoid, they're using a leak detection pump to either create a vacuum instead of using the vacuum from the engine, or they'll even pump some air in there to pressurize the system. Here's an image of a leak detection valve. So we talked about fuel trim, misfire are continuous monitors. When those codes set, those are going to be high priority DTCs. All the rest of the tests, they're going to attempt once per drive cycle as long as the conditions are met. If the test is interrupted, it's not going to make a second attempt at running the test. It's just not going to run it for that drive cycle. If you're trying to get the test to run, drive it for about 15 minutes, shut the car off, wait 10 seconds, start it up, try driving. If it didn't complete the test, it's probably not going to do it after about a 15-minute drive. And the manufacturers each have their own sequence of tests. So this is our 16-pin OBD2 connector. This is where, again, it gets really weird. This connector is supposed to be on the driver's side, visible from the driver's seat, X number of centimeters from the steering column. And you're going to find vehicles that you can put your head on the seat, push down, look underneath there, and you just can't see it. You have to look around for it. Volkswagen for a time put it behind the ashtray, or they put it behind this one, the plastic cover. You had to pop it off. So it's not always visible, even though it is supposed to be. It's not always on the driver's side, even though it is supposed to be. The pins, what I want you to notice in this lower right corner, if you can see it, starting in about 2007, 2008, the CAN, Controller Area Network, became the mandatory data that all the manufacturers have to use for OBD2. It's going to use two wires for communication, and that is pin 6, which is CAN high, and pin 14, CAN low. However, it also needs to have a good ground, so you need to check pin 4 and 5. For some reason with this CAN system, if pin 16 does not have battery voltage, it won't communicate. When I was working with the Department of Ecology in the state of Washington, and we had our emission test program and our OBD2, most of the OBD2 vehicles that had no communication, it was because the fuse was blown to pin 16. And on a lot of them, it is the same fuse for your power port that was on there. So dig the panty out of there that's got it shorted out, replace the fuse, and you have communication. So if you're working on a OBD2 system with the CAN, check pin 16 first. If pin 16 is good, what I like to do is put a lap scope on there. I put my black lead to pin 5, which is a signal ground, one channel to pin 6, the other channel to pin 14, and watch to see that those two signals look like a mirror image of each other. We went to a 5-digit code. Our first is going to be a letter, so P is powertrain, B for body. That's going to be your AC, interior lights, things like that. Powertrain, engine, transmission. The Z for chassis is going to be suspension, analog brakes, and then the U is for communication between those different computers. Second digit, most of them that you're going to be seeing are going to be P0 or P1. If it's a P0 code, that's generic. It's going to be the same code for all the OBD2 equipped vehicle. If it's a P1, it's going to be manufacturer specific, so that can be unique to that particular vehicle or that particular manufacturer. P2, again, is supposed to be the generic, same as the P0. When it gets to the P3, this is where it gets kind of weird. P3000 through 3399 is manufacturer specific, but from P0 through 3400 to 3499, that again is generic, same as the P0. Third letter starts breaking it down to the individual systems. So P4, we talked about it, P420 was the catalytic converter. The P300 is our misfire. Then you get your different ones. The P1000 code, I've only seen that on Ford. What that meant was readiness monitors are not complete. If you clear codes on there, you'll have a P1000 until all the readiness monitors are complete. then the P1000 will go away. So that actually was not a DTC. If you want more information on codes, this was a really cool website. It was a whole lot more information than I ever wanted to know about OBD2 codes, but if you want information on it, there it is. Last two is where it breaks down to the individual systems. I don't get a whole lot into this. Vehicle comes in, check engine lights on, pull the code, diagnose the codes that there. I don't try to memorize them. It's just the ones I see a lot are the ones that I remember. Most of the codes require 2 consecutive failures before they set. Once the code is set, if the problem goes away, 3 tests of the problem not reoccurring, and the light will go out, 40 tests, code clears from history. If a misfire occurs at 15%, so severe enough to cause catalyst damage, the code will set the first time, EGR, multiple tests, it's going to average it to prevent false EGR codes. On the OBD2 system, when it sets a code, the problem occurs, it sets as both a current and a history code. Shut the car off, next test drive. If the test runs again and the problem is still there, it'll be both a current and a history code. If it runs the test and the problem's not there, the light's going to stay on, but it's strictly a history code. When a DTC sets, now this is with OBD2. Let's say that you have a low flow on the EGR system. Code sets. If another code sets, like you have an evap code or something like that, you only have a freeze frame for the first DTC that sets, and it's only for the first time that the DTC sets. It will not be updated, except for the high priority DTCs. And that's going to be a fuel trim or a misfire. So if you have that EGR code and then a misfire occurs, the freeze frame data will be replaced with the misfire code. The misfire data is available or accessible with a generic scan tool. When you go to clear codes, it will clear your freeze frame data. So if you think you will need that freeze frame data, make sure you get that before you clear the codes or clear the emission related data. When you put a scan tool on the vehicle, if you have one of the more expensive scan tools and you identify make, model, and year of the vehicle, the data that you're going to get is the manufacturer's data, not the OBD2. Freeze frame data with the manufacturers, so like for GM, if that computer is capable of setting 74 codes, it can record 74 freeze frames. The other thing that GM does, each time the code resets, they refresh the freeze frame data. So when the vehicle comes in, if you go to the code on the OBD2, the freeze frame data is from the first time the code set. If you go into the manufacturer code list, the freeze frame is for the last time the code set. Prior to 1995, emission warranty was 5 years, 50,000 miles. Starting in 1995, the emission warranty went to 2 years, 24,000 miles on emission components, except for the catalytic converter and the PCM. California, they do their own thing. They went to 3 years, 50,000 miles for emission, and then 770 for the major emission components. Their major emission components covers more than the CAT and the PCM, but I don't know how much more. If you've looked at the back of Subarus, they have a PZEV on there. That is not a model of Subaru. The partial zero emission vehicle is a California rating. What the PZEV means is that the vehicle has to meet the federal super ultra low emissions for that vehicle, and it can't have any leaks on the evap. So not even 10 thousandths leak has to set a code. On a PZEV vehicle, it has to be warranted to be clean for 15 years, 150,000 miles. If you've used the scan tool, you probably didn't even know that these were modes when you went into the data list. That's mode 1. If you pulled up freeze frame data, that's mode 2. Looked at the codes was mode 3. If you cleared codes, that was mode 4. Mode 5 is going to give you the details of the oxygen sensors, breaking down each one, fuel trims, and that information. Mode 6, this is the one that a lot of people don't know about. That's going to give you your test results, and we're going to take a look at that on our next slide. Mode 7 is going to be pending codes. That means it failed the first test, waiting to see if it fails 2 tests in a row for whether it's going to set a DTC or whether it's going to clear from history. Mode 8 is control of onboard. On some of the vehicles, you can command it to run an evap test. And mode 9 is the VIN for that vehicle. Mode 6, this is the TID, the test identification, and the CID. The test is for a particular emission component. The one we're going to take a look at is the EGR. Then there's multiple components to this test. It's in hexadecimal. So looking over here, TID 07, and then the component ID, you see 07, 08, 0A, 0B. And we're going to look at this 07, 0C, and this is the EGR with the mass airflow sensor. Test ID 07, component 0C, minimum value is NA, doesn't matter. I'm assuming this is going to be going into negative numbers. Maximum is 0. This one actually had 65,491, obviously failed. Ran the second test on here, which was TID 07, component ID 0D. We'll go backwards, and here's our 70D, and this is our deceleration test. No minimum, maximum of 1, another 65,000 number, and failed the test. Where I use this the most, or where I have my students use this, is we get a vehicle that comes in, has low flow on the EGR, so they go through, they clean out the EGR passage, get the carbon out of there, take the vehicle out for a drive. I have them watch the readiness monitor. When the EGR readiness monitor goes to complete, then we come in here and we look at the mode 6. If it has, like a minimum of 0, maximum of 13,632, and they had 13,540, it's going to say pass. But they're right up there at the edge of passing, which means there's still a lot of carbon in there that they need to get cleared out. So pull it back apart, let's clean it up some more. Some manufacturers with the mode 6, they make you look at it in hexadecimal, and man, it is a pain to try to deal with these. There's other scan tools that are out there that with the mode 6, they actually interpret it for you. So they'll tell you, hey, here's your test for EGR, and then they'll even color code it for green if it passed the test, or red if it failed the test. If you're working on misfires, this data list that's in here is your misfire counter. Hopefully the manufacturer put this in here. They are required to put the misfire data in there. However, they're only required to put it into mode 6. And mode 6 is a pain to use. Hopefully the manufacturer gives you a data list like this. When you take the vehicle out, watch this misfire, and you'll oftentimes see that, hey, it'll go to 1 or maybe 2, and then after a while it goes away as it's going through and counting. To have an occasional misfire happens quite often. When you come and look at this and you see cylinder number 2 has 33,449 misfires, and cylinder number 5 has 368. Chances are there's no misfires at all on cylinder number 5. What happened is when the misfire in cylinder 2 happened, it created an imbalance that fooled the computer to think cylinder 5 was misfire. Look at your misfire. Look at your one that is the highest number. Concentrate your repair on that one. When you get that fixed, chances are you'll fix all the other misfires too. If you didn't, then you have to go on through and do it. And this is obviously the manufacturer's data list. And one of the reasons I have this on here is because you have this FC tau, which is unique to Toyota. And this FC tau is when you're going down a hill, decelerating, the computer's going to shut the injectors off. It's got a timer in there. It's going to look at the temperature of the catalytic converter, or it's actually going to calculate the temperature. When it thinks the catalytic converter is about to cool off, they'll actually re-enable the injectors to keep the catalytic converter hot. I hope you learned something from it, and I'll see you the next time.